Example 1 here on hypothesis testing is taking a look at the binomial hypothesis test. So we've been given our distribution and we observe x equals 6. We want to test at the 5% significance level if p is larger than 0.4. So as this is a hypothesis test, let's define our hypotheses. So we have h0 here and h1. And remember, for a binomial hypothesis test, we're testing the p parameter here. Okay, so p and p again. Now our h0 is that p is equal to 0.4, and h1 is what we're actually testing for here, which is p is larger than 0.4. So p is larger than 0.4 is our h1. We know the significance level is 5%, so therefore alpha is 0.05. So all we need to do now is test the evidence. So we observe x equals 6. So therefore, as this is greater than, we're testing our evidence here. That's the probability that x is greater than or equal to 6. And this is equal to 0.1662. So just use your calculator to obtain this value. And now we compare this to our significance level. So this is greater than 0.05. So we are more likely than the significance level to get the data we observe. So therefore, we do not reject h0, we accept h0, and we say there is insufficient evidence, so insufficient evidence to suggest that p is greater or larger than 0.4. So to suggest p is greater than 0.4 there. Okay, so that gives us the solution to example 1 there on hypothesis testing. Moving on now to example 2 here on hypothesis testing, which is taking a look at the normal hypothesis test. So the amount by which the train Nicola takes to work is delayed is normally distributed. Observations over a number of years show this delay has a mean of 5 minutes and a standard deviation of 2 minutes. Nicola believes this has changed. If she is delayed by 10 minutes on a Friday, is she right at the 5% significance level? So she's delayed by 10 minutes on Friday. Is she correct at the 5% significance level? So before we do anything here, let's just identify whether this test is one-tailed or two-tailed. And the clue here is in the wording of the question. We're told here that Nicola believes this has changed. So in this case, she doesn't suggest that this has increased or decreased, just that there's a change. So that tells us this is a two-tailed hypothesis test. So our hypotheses here will be h0 and h1. And remember, for a normal hypothesis test, we're using the Greek letter mu here to represent the mean. So that's mu and mu again. And if we just quickly define the distribution here, well, we're saying x is a normal distribution with mean mu, and variance here, well, the standard deviation is 2 minutes, so variance will be 2 squared there. Okay? So in that case, using the evidence we've been given, she believes the delay has a mean of 5 minutes. So we're saying mu is equal to 5, and as this is two-tailed, that's going to be not equal to 5. Okay? The significance level here, we're told, is 5%. So alpha is equal to 0.05. However, this is a two-tailed test, so we're looking for a probability less than half of the significance level. So therefore, 0.05 divided by 2. So that gives us 0.025 there. Okay. The observed data that we have is that the delay is 10 minutes on Friday. So what we've got here for the observed data, is x equals 10. Okay. So now all we need to do then is find the probability here. So therefore, what we're looking for here is the probability that x, our distribution here, is greater than or equal to 10. That's the observation that we've got here. So if we simply calculate this on our calculator, what we find here is this is equal to 0.0062. So 0.0062. And 0.0062 is less than 0.025, this value here that we're comparing it to. So in that case, we reject H0. So therefore, we reject H0, and we say there is sufficient evidence. So if we write something full here, there is sufficient evidence to suggest that the average delay has indeed changed. Okay. So there we go. So that gives us the solution to example 2 there on hypothesis testing.